This podcast is brought to you by the Environment Institute at the University of Adelaide. For more information, visit our website at www.adelaide.edu.au/environment.
Today I'm going to ask the question, how stable is our climate and how sensitive is it to future climate change? And the way I'm going to do this is by looking into the past. So I'm going to talk today about some of the recent advances that we've had in at looking at past climate change and how it bears on what we might expect in the future. So why study past climate change? As Martin said earlier today, it gives us a window into what might happen in the future. And firstly, it establishes a baseline from which we can look at modern climate change objectively. Is it unusual? Does it fit within the natural variability that we can see in the past? Is it, can we isolate whether it's caused by us or not? Secondly, it helps us identify the causes of climate change when we can look back through a long period of time and compare it against things like volcanic eruptions, CO2 changing in the atmosphere, or the changing amount of sunlight the Earth receives in different latitudes. We can find out what's causing the climate change. It also allows us to determine the sensitivity of an area to climate change. So when we look back at climate changes that have happened in the past, we can get an idea of how sensitive in terms of the magnitude that we might expect of climate change in an area. And lastly, it allows us to look for times in the past when we've seen climate events occur like we're seeing today. So we can compare, look into, perhaps get a glimpse in the future as to what might happen if things continue the way they are at the moment. So the research I'm going to present today is mostly on deep sea cores. So unfortunately, I don't have the spectacular slides of Central Africa that Martin has. So there's going to be a lot of text, but hopefully we'll get the idea. So as Martin mentioned earlier, the traditional view that we've had for the past century or more is that we've slowly lurched over the last million years or so from an ice age world into an interglacial world and then back again. And this is because it takes the Earth a long time to build up ice sheets. You've got to snow over many years, and that's got to solidify and turn into ice. And it also takes a long time for ice caps to melt. But something that we've discovered in the last 2 decades is that we've discovered that in times of the past, climate can change very rapidly. So this has become a topic of some concern for us. How possible is it that we can dramatically go from one state of a climate to another in a very short period of time? And what would the consequences be to us if that actually occurred? So that's what I'm going to talk about today. In particular, an event that happened in our recent geological past called the Younger Dryas event. And it's called the Younger Dryas event because it's the youngest of 2 events, and named after the Dryas flower, which is an Arctic flower that is found in pollen records during periods of ice age in Europe. The Younger Dryas event was a very rapid reversal of temperature when Europe was plunged back into an ice age at the end of the last ice age. So there was a warming and then a very rapid decrease in temperature. And this occurred about 12,000 years ago, and it lasted for 1,500 years. So what did it look like? How severe was it? This is an ice core record, and it's only been the last two decades that we've had some absolutely spectacular climate records recovered from ice cores, and these have completely revolutionised our view of how climate's changed in the past million years or so. They've given us an unprecedented view into how climate changes and when and why. This one comes from the ice cap on Greenland, and on this axis here we've got the ratio between 2 isotopes of oxygen. One's heavier than the other, and all this reflects the negative at the bottom and the positive at the top is that when it's cold, the snow is more negative. It's easier to rain out the lighter isotopes. So what we see here is over the last 25,000 years, the ratio of these isotopes has changed. This period in here, about 20,000 years ago, we call the last glacial maximum. It's the last one of 7 or 8 severe glacial maxima, when an ice cap basically the size of Antarctica formed over North America and then melted again. So about 20,000 years ago, this was at a maximum. Sea level was about 120 metres lower than present. Things warmed up, and then over a period of a few decades, temperature dropped by as much as 10 degrees in Europe. And this particular event has fertilised the imaginations in Hollywood and spawned a rather dreadful movie called The Day After Tomorrow, which is modelled on this precise event, except they compressed everything into a few weeks or months that what took decades or centuries to occur. I think they even had an ice cap coming down to, I think Long Island is the moraine of this ice cap, and I think they had an ice cap forming in weeks as well. But so what causes this? What's the reason why climate can change so rapidly? And the reason is that this is a grossly simplified cartoon of the way the world's oceans circulate over very long periods of time. And what the ocean does is it transports heat and salt from areas where the water's more dense to where it's less dense. And this occurs over many thousands of years. So there's an inequitable arrangement on the planet where the net amount of rain in the Atlantic Ocean is negative. And it's the saltiest ocean. So when the westerly wind blows across Canada and across the Atlantic Ocean, it actually evaporates more than it rains. So the water actually sinks and makes its way around the planet slowly. And this actually pumps heat up into the North Atlantic Ocean. And this is what keeps Europe basically ice-free, when just across the other side of the Atlantic there's an ice cap on Greenland. If you turn that heat pump off, you get an ice age in Europe. So there's a net release of heat into the atmosphere at this point that's equivalent to about a quarter of what it receives from the sun. So it's an enormous amount of energy. So the question I ask is, did we get this younger dry ice event in the southern hemisphere? And the younger dry ice event appears to be in a time when this heat pump in the North Atlantic Ocean is switched off. And that heat no longer is pumped into Europe, and you get an ice age. Temperatures drop by 10 degrees. And many people think that this had global consequences, that the whole planet experienced this decrease in temperature. And it has great consequences for the way we view climate change, because if this is actually the case, then you can propagate climate change around the planet virtually instantaneously. So there's some profound ramifications from this. So do we see the younger dry ice event in Australia? The evidence is circumstantial at best. When we look at records of recovered from lakes and bogs in the Snowy Mountains and Tasmania, where we've got the pollen has accumulated over thousands of years, we see lots of bumps and changes as we come out of the last ice age up into what we call the interglacial warm period at present. Well, we can't really tell temperature very well from pollen, so we're not really sure whether this is good evidence or not. And where we've dated glaciers up in the Snowy Mountains in Tasmania, we don't see a moraine dumped by ice advancing at this time, and as you do in Europe. But this is really not great evidence because we don't have very tall mountains, so they're not very sensitive to capturing small amounts of temperature change. But what we do have, the best evidence is a moraine out on the coastal slope on the coastal plain of the west coast of South Island of New Zealand. There's quite a famous moraine called the Waiho Loop on the Waiho River. And it's where the Franz Josef Glacier, which is one of the two famous tourist glaciers the three tourist glaciers in Tasmania, in New Zealand, where the Franz Josef surged out and increased its volume by 2 or 3 times. So this has long been thought of as a candidate for recording this global cooling. And in a quarry near the Franz Josef village, where you can stay if you go there, logs have been pulled out from underneath the glacial debris, and these have been dated at almost exactly 13,000 years. So it's right on that cusp of when you'd expect a younger dry ice event to have occurred. Here's the Franz Josef Glacier coming down here in the background. Franz Josef Village is in here, and this is the Waiho moraine, the Waiho Loop moraine coming down through here, and it's about 90 metres tall. It's you can't miss it, and it's a very prominent feature. And this was on the cover of GSA Today a few years ago now, and this is about the time when famous scientist by the name of Wally Broker started raising the issue of whether is it possible that if global warming occurs more rapidly than we expect, and we start putting fresh water from the melting Greenland ice cap and the Arctic ice into the North Atlantic, can we actually shut off the formation of this heavy water which pumps heat up into Europe? And this would have the paradoxical outcome of having an ice age in Europe at the same time as the rest of the planet bakes. So in order to test the evidence for the younger dry ice and to examine it objectively, we did 2 things. The first one was to use a new dating technique which has emerged in the past couple of decades, which is called exposure dating, to directly date the moraine instead of the debris that's underneath it, which has to be older, but it doesn't constrain it very well. And the second is to look at a deep sea core off the coast there and have a look to see whether we actually see a prominent cooling event in that ice core. So, exposure dating. The planet is continually bombarded by high energy radiation from outer space. There's a background radiation throughout our galaxy that originates from stars going supernova, and they eject very high energy particles, and these get sped up around black holes, and they're continually radiating us here on the Earth. Where we're sitting here, probably 1 every second is going through our bodies, and most of the time they're so powerful and so non-reactive they don't do anything. But when they do, if they hit an ordinary atom, they can have great consequences, like, for example, in playing pool, breaking the balls, you create some exotic elements that otherwise wouldn't exist on Earth. So you actually smash the atom and create some bizarre elements like beryllium-10. Beryllium is a metal used in the aeronautical industry, space-age metals, aluminium-26 and chlorine-36. And because these events occur so rarely, they create these rare isotopes at incredibly low rates of production. So only a few atoms per gram of rock per year, and that's not many. So therefore, we need a new technique that's called accelerator mass spectrometry. And accelerators have only been around for a couple of decades. Probably the first ones really commissioned in the mid-80s, late 80s. Or the ones that do this sort of dating anyway. And so this is a sort of a dating technique we've only just been able to start using in recent time. So exposure dating is based on the principle that the accumulation of these rare elements in surface rocks in the world is a function of time. So the longer you irradiate, the more you create. So for this dating technique to work, we need a rock that's never been at the surface of the Earth before. And glaciers are ideal for this sort of dating because they create fresh rock surfaces by excavating rock out of hillsides and by eroding the landscape. So we collected 10 boulders from across the entire Waiho Loop. And we used 2 different dating techniques. We used the chlorine-36 technique and the beryllium-10 technique. And we got very good agreement between both techniques. And when we determined the average age, it was 10,200 years. And this is significantly younger than the end of the Younger Dry Ice event, which is 11,600. So the actual advance of this ice out onto the slope was not associated with a cooling event in the Northern Hemisphere. And so it's an odd feature. And it's basically, there's been a paper published in the past year or two looking to see whether this was actually, the glacier advance was actually caused by a landslide onto the ice and therefore causing it to surge because you're protecting the surface from being melted. And it's a fairly controversial suggestion, but it would certainly explain why the advances happened, the ice advances occurred at a very strange and unusual time when we don't have advances anywhere else that I know of. So the second technique that we used, we collected a deep sea core in 1999, I think it was. There's a German research vessel came out called the Sonne, and on its 136th voyage, took the 11th gravity core off the coast. And this particular core is about 180 kilometres off the coast, and it's in the source region, the meteorological source region for the glacier. So it should be experiencing the same weather. So one of the things that makes this particular core ideal is that it actually has what we call outwash, which is clastic with sort of it's dirt debris that's been washed into the ocean from glaciers on land. So it allows us to, it helps us pinpoint where to match the core against what's happening on land. We dated the record using radiocarbon. So every 10 or 20 centimetres down, we picked out tiny little fossils. This is about 250 microns across, microns a millionth of a metre. These are tiny little zooplankton made out of calcium carbonate called foraminifera. And these zooplankton live throughout the world's oceans, and they're ideal for radiocarbon dating. And we also used a new measure to reconstruct what the temperature was like using just the sediment. It's much easier to use deep sea cores and the sediment from the deep sea to quantify temperature in the past, reconstruct climate change, than it is to do the same on land. There's very few techniques we can use on land to get very high quality records of climate change. Pollen tells us what vegetation was doing, but it doesn't tell us doesn't quantify what the climate was like. So what we used, there's these tiny little marine algae. These are nanoplankton. This is about 5 microns across. This is Emiliana huxleyi, named after Emiliana was Cesare Emiliani was a famous geochemist. And there's a tiny sphere of calcareous discs, these little discs made out of calcium carbonate. And these little beasties, for whatever reason, they produce 2 chemicals that change, the ratio between them changes with temperature. And it's quite precise. When it's colder, it makes more of one, and when it's warmer, it makes one of the other. So this is related to the biology of the organism, of the animal. So we extracted these chemicals called alkanones from the sediment and analysed their ratio through time. And this gives us temperature to within about 1 degree in the past. So here's the record I showed before. This is the Greenland ice core. And as you can see, this is 5,000 years at the top. Probably hope you can see that at the back, about 50,000 years at the right-hand side. And this is a period of stable climate in here from about 10,000 years ago. And here's the Younger Dry Ice event I was talking about, and the last glacial maximum about 20,000 years ago. So this is the climate as we see it represented in the North Atlantic and through Europe. And this is the record that we get out of Sonne 136 GC11, the core of New Zealand. In the period before what we call the last glacial maximum, we've got some very highly high amplitude, high frequency changes in temperature. And then we've got a long period of cold during the last glacial maximum, and then quite a rapid warming after the ice age. and then a sort of almost a monotonic increase in temperature up to about 11,000 years ago, and then a cooling towards the present. And this temperature is actually higher than it is today off the coast of New Zealand. And this is at a time when CO2 in the atmosphere was about 2/3 of what it is today. So here's a time in the past where we've got warming without any association with carbon dioxide changes in the atmosphere. And this time of about 10 or 11,000 years shows up in other cores around Australia and New Zealand. So what we're missing is this rapid decrease in temperature that we see in the North Atlantic, called the Younger Dryas event. So this is fairly damning evidence that we don't get the same event that we get up in the North Atlantic. So to summarise this evidence, exposure dating of the Waiho Loop indicates that it's occurred 1,500 years after the end of the Younger Dryas, and a high-quality record of temperature shows that we didn't get the same cooling down in this part of the world. And we also have evidence that about 10, 11,000 years ago it was warmer than present, and this is not associated with any carbon dioxide changes that we know of. So this is an important thing to think about, that we have enormous amounts of energy being transported around by our oceans, and when these ocean currents change, they can completely overpower the effect of what we see from carbon dioxide changing in the atmosphere. This can completely dampen or amplify what we get from the present climate change. So we can expect climate change to be very regional and even be negative or positive in some areas. And finally, the abrupt change that we see in the North Atlantic is not global. So we have to look at what the causes of this event are, because they're not associated with atmospheric changes like carbon dioxide or water vapour. So what does this mean for our climate? It means that we're going to have to take a lot more of a regional approach to looking at the causes of climate change. So the second part of the talk, I'm going to ask the question, how sensitive is our climate to climate change? The best time that I can think of to go back and look and ask this question is the greatest global warming that we've seen in our recent geological history. And this occurred at the end of the last ice age, as I showed on those figures before. And this is at a time when the carbon dioxide in the atmosphere increased by 50% in only 10,000 years. And parts of the planet warmed by as much as 20 degrees. And throughout the mountains of the world, as much as 10 degrees. And but this temperature change, as I said before, is highly regional. So I asked the question: how did Australia respond to this global warming? What was the temperature change across our region of space? So to answer this question of what was our ice age climate, we conducted a regional survey of the oceans around Australia. And to do this, we collected data from 165 cores that have been collected and studied over the past 30 or 40 years. We collected all the data together and added some new ones in where we could fill some gaps. And for each of these data sets, we determined which level was corresponded to the last glacial maximum, the last ice age. And we used the best dating techniques that we could find to do that. We used radiocarbon. We also used some techniques that just correlated based on the types of animals that were living in there at the time in order to determine when that age occurred in each core. Because we can't directly measure what the temperature was from these ice age sediments, as we did for the other core, we've got to use a proxy. We've got to use some way of estimating temperature in the past. And it's really as simple as if I walk into this lecture theatre in the middle of summer and there's no jumpers, I can estimate what the temperature is outside. But if I come in here and everyone's wearing coats, then we can certainly estimate that we're probably in winter. So we use some fairly interesting techniques. The one that we use here in this particular technique, in the particular study, we used these tiny little calcareous fossils that I talked about before called planktonic foraminifera. There's 45 different kinds of these throughout the world's oceans. And each one is found only within a narrow temperature range. So if we're talking about polar bears, for example, you don't find them in Sumatra or in Africa, and you don't find elephants in Antarctica. So each of these has a particular temperature range. So when we actually put them together as an assemblage, we can accurately determine temperature to about 1 degree again. So if we look at what the modern ocean is like, the first thing you'll notice in the tropics up here is this huge pool of warm water that's greater than 28 degrees in temperature. And the movement of this body of warm water backwards and forwards across the Pacific is what's responsible for the El Niño Southern Oscillation. And down the east coast of Australia, we have the bending of these isotherms down the coast here. We've got a current, the East Australian current, which carries warm water from the Coral Sea down as far as Tasmania and keeps the east coast relatively warm. And also down the west coast, we have a current called the Luan Current, which carries warm water from Indonesia that leaks through the islands up here and comes all the way down to Perth and sometimes gets around the edge down here. So if we look at the temperature estimates that we get for each of the cores and we compare them to what the temperature of the ocean is today, we find that the coldest temperatures that we found were south of New Zealand. The difference between last ice age and present is as much as 10 degrees. Then we move up into the lower latitudes through the Tasman Sea around Tasmania. We get -3, -4, -5 degrees. And then we get up into the tropics. We find that temperatures only change by about 1 or 2 degrees. And when we use these temperature estimates to make a map of what the ocean was like, we just basically join the dots and contour around all these estimates. We find that this big pool of warm water up in the tropics has migrated out into the Pacific Ocean. So we've got a climate scenario pretty much like a perpetual El Niño across Australia. And you'll also notice that I've dropped sea level by about 120 metres here. So we've got the Torres Strait closing, we've got Bass Strait closing, and most of the Indonesian archipelago becomes a giant landmass, which prevents a lot of water from evaporating because there's a reduced area of sea to evaporate. So all these events conspire to dry out Australia. So throughout Central Australia, we had a great expansion in terms of the size of our desert. So there are dunes along the Murray as far up as Albury that relate to the last ice age, even the Blue Mountains, and in Tasmania. We find that the East Australian current is still operating. There's still warm water up here, and it's still coming down the coast of Australia, maintaining those relict rainforest remnants, the warm temperate rainforest that we still see there today, what they didn't disappear. And we find that the Luan current switched off. There wasn't warm water coming down the coast here. And in fact, we're even getting upwelling of cold water off the West Australian coast. And this doesn't happen today, but it happens in all the other continents in the southern hemisphere on their western coasts. You get the wind pumping, blowing across the continent and pumping up cold water. And so this would have been a great fishery in the middle of the last ice age if there's anyone around to be fishing. And we also find that there's much colder off the coast of South Australia and Victoria. There's the cold water from Antarctica was moving further up as much as 5 or 7 degrees further north than it is today and hitting the coast up here. So that would have been quite a nasty place to live. But the biggest change we see is off the coast of New Zealand where the currents have moved right up to the point where there's probably polar sort of temperatures off the southern part of New Zealand. And we know that there's an ice cap on the southern part of New Zealand, and so that the two lines of evidence match up there. So to summarise, we found that the tropics are least sensitive to climate change. The northern half of Australia is least sensitive to global warming. And the reason for this is because it's, the climate is already buffered in that area. It's pretty much as warm as you can get. If you warm up the oceans anymore, you cause more evaporation and you cause more cloud cover to form. And the cloud cover actually reflects sunlight back out into space. So it's thermostated, it's self-limiting. So even if the planet warms up, it can't warm up much more in those areas. In the southern part of the continent, it's drier, you don't get as much cloud cover, and the ocean has less of an effect on climate. So in particular, Canberra would be one of the most sensitive areas to climate change because of this. And we found that the sub-Antarctic is the most sensitive. It experiences the greatest amount of warming during climate change. And this has very important knock-on effects because because the sea ice is very sensitive to small amounts of temperature change, you can expose very large amounts of the sea to carbon exchange, and also the lack of sea ice won't reflect. Lack of sea ice will change the albedo of the reflectivity of the Southern Ocean, so that you can get a lot more of the solar radiation being absorbed into the Southern Ocean than you would otherwise. And ultimately, of course, it contributes to melting Antarctica, which will rise sea level. So to conclude for tonight, what we've seen from our records that we're actually in a stable climate mode at the moment. But we've seen that in the past, particularly during the last ice age, the climate in Australia and in other parts of the world is highly variable and could change over decades to centuries. And one of the things that we found from studying the Younger Dry Ice event is that if Greenland does melt and floods into the North Atlantic and Europe is plunged into a devastating ice age, then we'll actually be pretty much safe and sound here, and we'd probably end up with climate refugees coming down here, boat people from Europe. And from studying the last ice age, we found that the southern latitudes are the ones that we should perhaps be focusing most on in terms of our mitigation efforts, and particularly our monitoring efforts for what's going to happen. Okay, thanks.